But now, somewhere in the Milky Way, a planet's sky may be glowing with the chemistry of life, and our telescopes might already be seeing the fingerprints. We haven't seen aliens, no cities, no radio messages, nothing like that. But over the last few years, scientists have started to glimpse something much more subtle and maybe even more important: biosignatures, faint chemical clues in the light of distant worlds that whisper, something alive could be doing this. So how do we hunt for life on planets we will never visit, around stars we will never approach, using light that left them years ago? And how close are we to an answer? Let's start with what a biosignature actually is. A biosignature is any measurable sign that could only reasonably be produced by living things, or is best explained by biology. That might be a gas in an atmosphere, a pattern of colors on a surface, or even a weird imbalance of chemicals that, left alone, should have reacted away long ago. On Earth, our most obvious biosignature is literally in every breath you take: oxygen. Free oxygen gas is incredibly reactive. It doesn't like to stay as oxygen. It loves to rust metals, combine with hydrogen, and burn carbon. If life disappeared from Earth tomorrow, our oxygen-rich atmosphere would start collapsing chemically within a few million years. The only reason we have so much of it is because photosynthetic life is constantly pumping it out. So scientists ask a simple question: if we saw an Earth-like amount of oxygen on a distant planet, plus other supporting gases, would that be enough to say, life is probably there? To even try to answer that, we first have to detect the atmospheres of these distant worlds, these exoplanets. And that is already a wild trick. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before it reaches us. That thin ring of air around the planet acts like a filter. Different molecules in the air absorb different colors of light, leaving a barcode-like pattern in the spectrum. This technique is called transmission spectroscopy, reading the chemistry of a world from the way it dims its star. Space telescopes like Hubble and now the James Webb Space Telescope are built to measure those spectroscopic fingerprints with insane precision. Imagine trying to see the color of a moth's wings as it flutters in front of a spotlight from thousands of kilometers away. That's the level of subtlety we're dealing with. But what are we actually looking for in that light? One classic target is the combination of oxygen, or its photochemical cousin ozone, together with a reducing gas like methane. On a lifeless planet, those two gases should quickly react with each other and vanish. Yet on Earth, life keeps both topped up at the same time. That kind of chemical disequilibrium, an atmosphere out of balance, is one of the strongest hints biology could be at work. Another big candidate biosignature is methane itself. Methane is produced by volcanoes and geology, yes, but on Earth, most atmospheric methane comes from microbes in living systems: wetlands, cows, termites, even tiny organisms in the ocean. If we found a rocky planet in the habitable zone with methane that couldn't be explained by simple geology, that would be very interesting. Not proof, but a big flag. Scientists also think beyond gases. Reflective patterns on a planet's surface could reveal something like vegetation. On Earth, plants have a specific red edge in their reflection. They absorb visible light for photosynthesis but reflect near-infrared strongly. If we watched a distant planet and saw its reflected light change as it rotated with a repeating plant-like red edge pattern, we'd have to ask, what else besides life does that? And then there are more exotic biosignatures. Molecules like dimethyl sulfide produced by plankton in Earth's oceans, complex organic hazes that might hint at microbial chemistry, even seasonal swings in atmospheric gases, like the way Earth's carbon dioxide dips slightly every northern hemisphere summer as plants leaf out, could be detectable with future telescopes. But here's the hard part: nature is clever. For almost every proposed biosignature, there's at least one potential false positive, a completely non-biological way to make the same signal. For example, you can get oxygen in an atmosphere if a planet's oceans are blasted apart by intense starlight and the hydrogen escapes to space. No life needed. You can get methane from hydrothermal vents and deep geology, again without biology. So the real challenge is not just seeing a weird chemical, it's ruling out all the non-living explanations. That's why scientists talk less about one magic biosignature and more about a biosignature context. What's the planet's mass and size? How much energy does it get from its star? What is the star like? Calm and sun-like, or violent and ultraviolet bright? What other gases are present? All of that matters. This is where upcoming missions become crucial. The James Webb Space Telescope is already probing the atmospheres of some super-Earths and mini-Neptunes. searching for water vapor, carbon dioxide, methane, and more. The European mission Ariel is coming, designed specifically to survey hundreds of exoplanet atmospheres. And further out, concepts like NASA's Habitable Worlds Observatory and ESA's LIFE mission aim to do something even more audacious: directly image Earth-sized planets around Sun-like stars, and split their light into spectra. Direct imaging means blocking the star's overwhelming glare, like holding your hand up to block the sun so you can see a firefly next to it. With advanced coronagraphs or even giant star shades flying tens of thousands of kilometers from a telescope, we could for the first time see pale blue dots orbiting other stars and read their atmospheric barcodes in detail. If we find an Earth-sized planet in the habitable zone with water vapor, with oxygen and ozone, with a whiff of methane, maybe even with seasonal variations in those gases, at what point will scientists stand up and say, "This is it. This is very likely life"? How strong does the case have to be when we can't go there and scoop up soil? That's the tension at the heart of this search. We are detectives working entirely from the light of distant worlds, building a case molecule by molecule. The first confirmed biosignature will not come from a single dramatic line in a spectrum. It will come from a careful global picture of a planet that just won't make sense without biology. And when that happens, when we can finally point to a star in the night sky and say, around that star on that tiny world, chemistry woke up and never went back to sleep, everything changes. Life will have gone from a local accident to a cosmic pattern. So here's the question that hangs over every observation James Webb makes, every future telescope we launch. Will the universe turn out to be mostly quiet rock and gas? Or will biosignatures start appearing everywhere we look, telling us we've always been part of a living cosmos? If you want to be there, the day we decode that first unmistakable signal from an alien biosphere, stay with this channel, subscribe, and we'll follow the light together.